Thank you. So, as Ben said, my name is Seongbin, and I'm a first-year PhD student at UCLA. And today I'll be presenting our paper, Chimera, Creating Digitally Signed Fake Photos. So this paper was published to Usenix 2025, and it was done in conjunction with professors Tian, Kadambi, and Zihad Baksh. I would also like to thank my collaborators, Sasha, Jinghui, and Hossein, before I present. So I compiled a few headlines about image generated by fake AI. In this paper, we use deepfake to mean fake images generated by these types of image generators, but specifically images that look like real images. But anyways, so I compiled a few headlines, and as expected, they're mostly negative. So as these headlines suggest, fake image-based misinformation has negative effects throughout society. For example, recently, Grok AI was caught generating nudes of real people. These deepfakes are also used for political smear campaigns where people can frame a political candidate or celebrities for saying something or doing something that they've never done. Additionally, there have been reports of people falling for deepfake-based romance scams, and there has been real-world monetary effect on people who fall for these generative AI-based scams. So as these headlines suggest, that it is important to know whether an image or video is real or not. However, this is not always easy. So on this screen, I compiled a few examples of deepfake images. On the top left corner, we have a few people. And believe it or not, they're all fake images generated by StyleGAN. And on the top right corner, we have a face swap application where we can swap our faces with anyone we desire to. And these can be used, as I said, for smear campaigns and things like that. On the bottom left, we have a face tuning application where we can smooth out our skin, give ourselves fuller lips, to basically create altercated versions of ourselves on social media. And lastly, I put this slide in, or this image in, because this image did go viral on social media, but as expected, it is fake, and the original image is on the right to it. So because these images are getting realer and realer, how can we tell an image is fake? One way to do that is using deepfake detectors. So deepfake detectors are statistics or machine learning-based models where it's a classifier, where you take an image and basically output whether an image is real or fake. However, these detectors work well initially, but as generators' capacity gets better and better, the job of the detectors gets harder. So in order to detect the fake images, the detectors must get better, but then if the generator gets better, then the detector has to get better again, and so on. So these detectors and generators are caught in a never-ending arms race. So an alternative to this, alternative to this is verifying the realness of an image. And the way to do this is via media provenance verification. Media provenance verification is a way to cryptographically sign images at capture time. Standards like C2PA already implement this, and many companies have agreed to this standard. So in C2PA, what happens is, let's say Linda, our user, takes a photo using her C2PA-enabled camera. Then her camera cryptographically signs her photo and embeds it into the metadata. And any edits made after Linda captured the photo is also embedded in the metadata. Then, if a end user comes across Linda's photo on the internet, they will have full information of whose camera it was taken from, or that it was taken from a camera at all, and also any subsequent edits made to this photo. So, however, these image provenance-based verification schemes also are susceptible to spoofing attacks via recapturing. So recapturing is basically taking a photo of a displayed image on the screen. So on the screen, we have an original image. Then we remove the wallet in the original image using a generative AI, display that fake image on a display, and then take a picture of that using a phone screen or a phone camera. This way, we can embed the real image verification, or that this photo was taken by a camera, into the metadata, except for that it's actually a fake image. It's just a picture of another picture. So here's another example. We have the original photo, then a deepfake version of that photo, and we can display that deepfake photo on a computer, take a picture of that, and there will be real image metadata embedded into this photo because we took it with a real camera. So you might think that it is easy for us to distinguish between real images and recapture images. So on this screen, this is actually taken from a work done by Liu et al. At UCI, which I will introduce at the end of this presentation. But anyways, on this screen, we have 8 real images and 8 recaptured images. So let's try to see which ones are real and which ones are recaptured. Maybe that's enough time. I highlighted the images that are recaptured. And as you can see, it's quite difficult to discern between real and fake. And if you got most of them wrong, that's probably normal because when Liu et al. Ran this study on, I think, 43 participants, they only found the right answer around 50% of the time, which is literally random. Another downstream effect this recapture attack has is that it can evade deepfake detectors. So basically, if we take a photo of a deepfake picture displayed on a screen, this actually, without any adversarial attack going on, this actually reduces the effectiveness of deepfake detectors. And as you can see on the screen, we tested it on 2 state-of-the-art, at the time, detectors. And especially for the fake images, we can see that the accuracy drops considerably. So mitigations to recapture attacks do exist. So for example, when you recapture an image, it actually creates something called a Moyer effect, which you guys probably have seen when you try to take a picture of a screen. It's basically like the colorful lines that you would see on your picture. So recapturing an image generates these physical artifacts, and these artifacts can be exploited by recapture detectors. And these detectors are, again, machine learning classifiers that detect whether or not an image is recaptured or not based on Moyer effect, as I said, something like edge blur or color aliasing. And these recapture detectors actually work quite well, but we can ask the question, is this enough? Is there a way for an adversary to exploit this defense as well? And for an adversary to do that, they must meet these 3 criteria. So for an adversary to create a signed fake image, they must fool recaptured image detectors, fool fake image detectors, and also it must be perceptually indistinguishable from real images, because otherwise the end user looking at this image will not believe that this image is real anyway. And all 3 of these objectives must be achieved before, or any alterations that we make to the image must be done before we take a picture of the image, because if we alter the image after we take a picture of it, there will be metadata that lets the end user know of any wrongdoing. So here, I'll go over some popular attacks against machine learning models and why they're not enough for our setup. So adversarial noise, for you guys who don't know, it basically inserts a very minuscule amount of noise that causes a classifier to classify an image incorrectly. So in the example, we have an image of a panda, which is classified correctly. But if we add some adversarial noise, the classifier starts classifying as a given with a very high probability. However, these adversarial noise attacks, though very, very effective, it doesn't survive the recapture process of taking a photo of the screen because the adversarial noise is too small and it doesn't survive that transfer process. Another type of attack is adversarial patch attack. And this involves putting a physical patch in the screen so that it would trick the classifier. And these patches, if constructed carefully, could be able to fool both recaptured image and fake image detectors, but the issue is that a patch is quite obvious and it is not perceptually indistinguishable from real images, and anyone who sees these types of image will know that there is something going on. So our attack successfully bypasses all three of these objectives, which I will go over right now. So the threat model for our attack is that we treat the recapture detectors and deepfake detectors as black box models. This means that we don't have access to their weights or anything, so we can't do like an adversarial noise type of attack that uses the weights. Additionally, the attacker is free to modify the generated deepfakes, but not after the photo is taken. And lastly, the attacker can control the whole hardware setup. So that would include the devices used, so the camera that we use to take the picture, and also the screen that we use to display the deepfake image. Additionally, we have control over the configuration of the camera, so that would be maybe the zoom or the focus. And lastly, we have control over the configuration of the screen. So that would be how bright the screen is or how far the screen is from the camera. So here is an overview of our work. We split it into two domains, the digital domain and the physical domain. So in the digital domain, we basically alter a generated image to be a bit adversarial. In the physical domain, we do some effects to make the image look good, and then after passing these two domains, we deceive both recapture detectors and deepfake detectors to get a cryptographically signed verified real image. So in the physical domain, we mainly focus on trying to get rid of these physical artifacts. So I did introduce Moyer effects earlier, but it's basically what happens when the pixel grid of the monitor and the camera's sensor grid is mismatched, and it is not parallel. And this sampling mismatch causes these rainbow stripes to appear in the image. And we can actually remove this by adding some blur in the camera. So for example, if we add too much blur to the image, the perception, we can't even tell what the image is, so this isn't good. But if it's too sharp, it will reintroduce the physical artifacts. There is a sweet spot in the middle that we found that doesn't have any obvious physical artifacts, but is also visually sharp enough for humans to discern what this image is supposed to be. And as you can see in the orange line, the FID score, which basically measures the similarity between the real image and then all of these recaptured images, is the lowest for this image in the sweet spot. However, the blue line is the accuracy of recapture detectors. And we can see that recapture detectors are still pretty able to detect that images in this range are recaptured images. So in the digital domain, we make modifications to the generated AI image so that it will also be able to fool these detectors. So here's an overview of our pipeline in the digital domain. In stage 1, we learn the recapture function. So whatever transfer that occurs from the raw deepfake image and then whatever function capturing that deepfake image displayed on a screen is using a camera. In stage 2, we take that the simulator for the recapture process and learn the inverse of that function. And lastly, in stage 3, we do inference using that inverse function. So in more detail, in stage 1, we basically want to mimic the process of recapturing an image from a fixed setup. So we do this by training a generative adversarial network, and we do this by trying to match the generated image generated by the generator to the true recaptured image, which we collect on our screens, or by taking pictures. And then once we have the recapture simulator, we freeze it inside the inverse generator training loop. So here, let's say the recapture function would be f. We try to find the inverse function, so f minus 1, so that the physical recapture process effectively undoes the adversarial image back into the raw, clean-looking one. So we do this by trying to map the original input image to the generated image through the whole pipeline. And lastly, once trained, the attacker would feed their chosen deepfake image into this inverse generator that we learned in step 2. And then this would create an adversarial image. This adversarial image is displayed on the screen and captured by a camera. So hopefully our inverse generator has learned the actual inverse function of the recapture process, and the recaptured image is in the distribution of real images, which would make the detector's job very hard. So here's some training details. We used 2 setups to test our method. The first one was just using an iPhone camera and a MacBook Pro display, and the second setup was using a machine vision camera and an LG Full HD display. And because the simulator is specific to the placement and characteristics of the hardware pair, to create our data sets, we actually fixed the camera display orientation. And lastly, the images that we displayed on the screen to take a picture of, they were obtained from the LSUN dataset, which has both real and fake images across 3 classes: cat, church, and horse. So we use Pix2Pix to do paired unidirectional image translation, which basically is trying to map an image from one distribution to another. And our generator was a unit architecture with 7 downsampling layers, and we operate in the 124 pixel space. So the loss function for training the generator was the GAN loss, which we get from the discriminator, and the L1 loss, which is used to try to match the pixel similarity, and the focal frequency loss, which we use to minimize the frequency domain forensic choices, which is used by recapture detectors. And we trained 3 recapture detectors on images, including those obtained using a hardware setup, just so we are sure that our defense is as strong as it could be. So here are the results. In the second column, we can see that recapturing an image actually alters the color scheme and the frequency of the raw image by quite a bit. However, if we generate an adversarial version of our deepfake image, then take a picture of that, we can see that the raw images and the recaptured adversarial image are more similar to each other. There is a failure case on the very bottom row, but we believe that because generative AI is getting better and better, if we train this again with current models, the fidelity will be better. So here's some quantitative results. So recapture detection accuracy dropped by a lot using our method compared to the baseline recapture spoofing attack. So for just recapturing an image, these recapture detectors were able to detect it by 90.8%. But using our method, we dropped it down to 26.7% across detectors. And the fake image detection accuracy, as I mentioned earlier, this is just a byproduct of the recapture process. And adding adversarial noise, we found that it doesn't affect this free deepfake detector evasion. So as you can see in the 2 sets of bars on the left side, the deepfake detection accuracy dropped for both of these models. And on the very right, we have 3 bars, and this is actually a deepfake detector that I fine-tuned with samples from our setup. So we just fed in recaptured images into this as well, so it would be able to kind of adversarially adapt. And we did this with setup 1. So we found that this actually helps performance in that it was able to detect fake images in our first setup pretty well. But in setups that it hasn't seen, it doesn't generalize to these. And it's pretty impossible to account for every single setup, so this type of adversarial training scheme must be thought a little bit more through to be effective against these recapture attacks. So all in all, the defender can layer both the recapture detector and the deepfake detector, and when we layer this, we found that the baseline recaptured fake images only have less than 1% success rate. However, our attack has 15% success rate of bypassing all defense layers and obtaining a hardware signature. And 15% might not seem like a lot, but this actually means that 1 in 7 fake images will bypass generative AI detectors, recapture detectors, and have a cryptographic signature proving that it's real. This means that the attacker only needs to try 7 times to create an image that everyone would believe to be true. So here are some mitigations to our method. So one way is to use depth information. Because screens are flat, we can basically use that information. And so screens are flat, but real scenes are in 3D. And we can use this mismatch and the depth information obtained by our cameras to basically identify if an image is fake or not. And this would require the LiDAR or time-of-flight data from our cameras. Another way is to use behavioral heuristic monitoring. So basically, to train Chimera, we need to take like hundreds of photos. And when we do this, we can basically flag any suspicious activity, or like the OS can flag any suspicious activity and report it and catch any adversaries using this type of method. So I'll go into more depth of a paper that actually implements this depth verification. So this paper is called Scoop, Mitigation of Recapture Attacks on Provenance-Based Media Authentication. This was done by Miles at UCI and his colleagues. And it was also submitted to Usenix the same year that our paper was submitted. So Scoop is basically done by comparing the ground truth point cloud, which you can get from the phone's depth data, and also by training a point cloud generator that will learn the expected point cloud of a taken image. And if there is any mismatch between the ground truth point cloud and the expected point cloud generated by this machine learning model, we can compare it and overlay it and flag if there is any wrongdoing. And if there's this mismatch, we know it would be a recaptured image. So Scoop is pretty realistic because most modern cameras and phones are equipped with a depth sensing ability. I think my iPhone can sense up to 5 meters, for example. And the overhead is that there's no runtime overhead at capture time because the verification is not done on the phone itself in this pipeline, but verification pipeline needs around 3 to 70 seconds of processing time because you need to generate the point cloud and like the expected point cloud and compare them. So to wrap up this presentation, I'd like to ask, are we good now? So using cryptographic signing architecture and also this type of depth-based verification, can we ensure that our images, if they are signed as real, are actually real? And with that, I'd like to end our presentation. Here are some QR codes for our paper and code, along with Scoop's paper and code. And thank you very much.
OK, so we have time for questions, if you want.
Hi, thank you for a very interesting presentation. This is quite cool. You said, made with your talk, that the attacker would have to try about 7 times to get successful. Is that, do you understand whether that's with 7 times of the same like base image? That is, if you just like perturb that image, do you get success? Or is it like, or do you not know?
So it's like, it would be 7. So basically, we just evaluate it with like a big data set, and we would say that 7 images, like 1 image out of 7 passed. So maybe it is we're not sure, like I'm not sure what is the issue of some images passing and some images not. But I would think that when an adversary is generating these fake images, they can try multiple times of just like tweaking details and just seeing if it would pass or not.
Right. Thank you.
Anyone else? Okay, thank you very much for your talk.